I am the out and out preacher, words and verbs and academic sermons. Come along with me, take my hand and do some learning.
Welcome. Let's do some math. In this video, we'll be looking at 3 areas of analysis in which research is currently being done. Now, of course, we won't go deep into these subjects, given the fact that we only have a limited amount of time, but we'll try to give a little sense of what each of these topics is about. We'll start with complex analysis, followed by dynamical systems, and then we'll end with partial and ordinary differential equations. Let's start with complex analysis. So what is complex analysis? It's the study of functions of the following form. It's a function f that goes from the complex numbers to the complex numbers. In general, we'll just call these complex functions. This is used in various areas of both pure math and in applied areas such as physics, chemistry, electrical engineering, and so on. In pure math, just a few of the places it's used is algebraic geometry, number theory, and analytic combinatorics. And some of the applications, as I mentioned, thermodynamics, hydrodynamics, and in particularly quantum mechanics. Now, what is the essential discovery of complex analysis that's really surprising and sort of powerful? It's the fact that you can say something about a complex function over a given area in the complex plane by looking at what happens on the boundary of that area. What I mean by that is if you have the complex plane, say here, and you've got an area, and you're looking at a complex function over that area, you can just look at the boundary, the sort of quote-unquote edge, as it were. If you know information about what the complex function is doing on that boundary, you can say what it's doing in the interior, which is pretty fascinating. So boundary information tells you about interior information. Now let's look at some of the essential properties of complex numbers just to make sure we're on the same page and know what we're talking about here. First, when we talk about the complex numbers, we're really talking about a plane where there are 2 axes. One axis is the real axis. The other axis is the imaginary axis. Every complex number is written of the form some real number plus some other real number, but that second real number is multiplied by the square root of -1, which we call I. Since that requires, in some sense, 2 dimensions, the real dimension and the imaginary dimension, we have a plane with 2 axes. Now, if we graph this number, x plus yi, where x is the real part, y is the imaginary part, and we do so on a 2-dimensional plane with real axis and imaginary axis, we'll get some point in the 2-dimensional plane. And now we can describe the complex number in one of 2 ways. We can do it in our Cartesian sense, where we have the x and the y as we've done. And notationally, we say that x is the real part. Then we say that the imaginary part is y. But if you've worked with Cartesian coordinates, and namely changing them to other coordinate systems, there's a good chance you've come across polar coordinates. And it's exactly the same here. We can look instead of x and y, which are Cartesian coordinates for this point, we can instead look at the length, or what we'll call the modulus, and the argument, or what we call the angle. These are exactly the same as polar coordinates if you've happened to come across those before. The modulus we can simply get by noticing we have a right triangle here, and using the Pythagorean theorem. It's simply the square root of the sum of the squares of the 2 Cartesian coordinates. So if you know the Cartesian coordinates, you can find the modulus. You can also find the argument. This is the arctan of this quotient. And how do we find that? Well, we just use a little bit of trigonometry. Here's a right triangle again. The tangent of this angle is the opposite, which would be y, over adjacent, which would be x. That sets up tangent of this theta is y over x, opposite over adjacent. And then, of course, we take the arctan or inverse tan of both sides to end up with this. Besides just having another way to write complex numbers, which can be very useful for a variety of reasons, it will become critical when we look at graphing complex functions, because we'll essentially run out of spatial dimensions that we can use, so we need another way to represent it. As an example, let's say we have a complex function that takes the complex number x plus yi to some other complex number, which is a plus bi. Both of these are complex numbers. One way to think about the function is it has 2 parts to it. It takes your x plus I, and namely it takes the coordinates, the x and y coordinates. And you can think of those being fed into a function that turns it into a real number, where that number is alpha. So there's one part of f, namely the real part, which gives you alpha. Meanwhile, there's another part which gives you beta. So a complex function takes, in some sense, two inputs, an x and a y, the real part and the imaginary part, and then using both of those inputs for two different functions, uses one function to give you a real part for the output and one function to give you an imaginary part for the output. Now let's think about how we might graph complex functions. First, let's start with the real case. Think about how we would ever come up with a graphing system for that, and then see how we might apply that same logic to the complex case. If we have a real number that takes a real number and then outputs a real number, the real numbers are one-dimensional. We talk about the real line. Each axis or line that constitutes your coordinate system is one dimension in a very simple sense. The real line gives us one dimension from the domain, and then since the real line is the codomain, that gives us one dimension in each case. If we add that up, of course, we get two spatial dimensions total. Say we have a function like f of x is equal to x squared. If we were to graph that, it would look, of course, like this, where I've indicated the domain real line in red, the codomain real line in cyan here, and we can see that a real number input 2 is fed into the equation or formula and gives us an output of 4. If we do that with every point in the domain here, and we plot all those points with first coordinate, the domain value, second coordinate, the codomain value, we get this line here. In the complex case, what we're doing is we're going from the complex plane to the complex plane. And as I said, it's a plane, so we have two dimensions for the domain, then we have two dimensions for the codomain. If we add that up, we're going to get 4 dimensions total, which of course is a problem. We can draw a two-dimensional coordinate system here because we have literally the plane that we're writing in and that you're watching this on is two-dimensional. We could even do three-dimensional with some perspective, since we can look at a picture and think of it or imagine it in 3 dimensions, because that's how we interpret things that we see for the most part, is in a 3-dimensional sense. And that's how we understand our surroundings in the spatial sense, is in 3 dimensions. But 4 dimensions is now a little tough. There are some fancy things you can do to represent 4-dimensional objects. And when I say fancy, I mean some really, really cool things you can do, especially when you start looking at topology. There's ways to represent 4-dimensional objects in formats that allow you to capture essential information. But in general, this is a very difficult thing to do. So how it's handled here with complex analysis is in the following, in my opinion, very clever way. Since we're limited to 3 spatial dimensions that we can either picture and think in terms of, well, maybe the 4th dimension should then be non-spatial. And what's used to represent it is, in my opinion, brilliant. We have a function from the complex numbers to the complex numbers. For the domain values, we'll actually represent those with 2 spatial dimensions in the traditional complex plane. For the sake of perspective, we'll lay that plane flat, or what seems like it is flat to us, as if this plane were sort of coming out of the screen at you. Then we'll represent one more dimension using space, and we'll represent it according to the modulus of a complex number. Now remember, the modulus is square root of the sum of the squares, so it's going to be a non-negative number. But importantly, it's going to be a real number. That means we can represent it using a real axis. So we have 2 axes here, and then we have another axis here. Finally, since we've used up our 3 dimensions, what we'll do is we'll represent the argument of the complex number in this way. We'll represent it using this color wheel, which to me is just so cool. The angle of the complex number, and remember, a complex number can be represented using either Cartesian coordinates, an x and y, or it can be represented using a modulus and an argument. The argument is an angle, and the angle can be represented via this wheel. For example, if we were to, let's say, have a real number that was positive, we would color it red. If we had an imaginary number, like let's say 5i, we would color that this sort of greenish yellow. If we had a strictly negative real number, we would color it cyan. And if we had a negative imaginary number, such as negative 17i, we would color it this sort of lavender deep blue. And of course, if you had a complex number like 1 plus 1i, something that had an angle of 45 degrees, you might color it this orangish yellow. To reiterate, we have two spatial dimensions that we use to represent the complex numbers in the domain. And then in the codomain, we use one spatial dimension and one quote-unquote color dimension, which is so neat. I can't get over how cool this is. Now, if you were to graph this, remember that z is going to be the modulus of the complex number in the codomain, the number that is mapped to. So this will give you some varying height off of the base plane. A graph of a complex function might look something like this, where the values here in the light blue could be thought of as having no height. They're very small. That is, their modulus, since they're so low, since they're so close to the base plane, that means their modulus is very small. That must mean that their corresponding values, their real imaginary parts, are very small. Now, we don't know which of the two is larger just in of itself based on the modulus. You could have a small modulus be down here and have a large, or let's say larger, real component than you had imaginary component, but that ratio is captured in the color. So notice here, these are light blue or cyan colored. That means that they must be corresponding to here. So a light blue flat area, or a number that is represented as light blue and very close to the plane, that is a number that's in the codomain. That number is going to be strictly or very close to strictly negative real, and it's going to be very close to the origin. Being close to the origin is represented by it being flat, by it being close to the base plane, and the color again is essentially where is it in the complex plane. If we look over here at, let's say, the purple, these purple values are now going to be something more akin to a negative, purely imaginary number, and they're going to be pretty large. So whereas something down here might look like, let's say, negative 1/10, something pretty close to the origin, or something over here will have a larger modulus because it's higher off of the base plane, and the fact that it's purple gives us that it's going to be around purely negative imaginary. So maybe it's something like negative 17i or something like that. So negative 17i might be a type of number found here. And then we have over here something more like negative 1/10, but real. Now let's do a little bit more computation to help settle this in your mind. Suppose we have the complex function that takes complex numbers x plus yi, and it sends them to the complex number given as follows. The real part of the complex number that is mapped to is just x times y, whatever this number is times whatever this number is. The imaginary part is then negative x, or negative what was the real part. Let's create a table to see how we might do some calculations to get a better sense of this function. Here we've listed the domain, and in general, a point xy, where x is the real number and y is the imaginary number. Then in the codomain, we've listed two ways to look at the number that gets mapped to. One way is the real and imaginary part. These are separately thought of as terms of Cartesian coordinates. And then in another case with the pairing, the modulus and the argument. Now if we take the general point xy, we know by this formula that the real part is going to be x times y, the imaginary part is going to be negative x. The modulus is simply the square root of the square of the 2, that is, of these two coordinates up here, which are the same as these. That amounts to this formula. And as we noted in a previous page, the argument is given by the arctangent of the ratio of the two. Taking a specific point, let's say the point with real value 1, imaginary value 2, this is a point in the domain. That will get mapped to via this formula. 1 times 2, because that's x times y, gives us 2. That's the real part of the number this complex number gets mapped to. The imaginary part is correspondingly -1. The modulus is going to be √5, and the angle is going to look like so. Now let's say we tackle just finding that point explicitly. Starting with 1 plus 2i, if we flatten the complex plane so that it's laying in a vague sense horizontal from our artistic point of view, there's a real axis and an imaginary axis. That point is going to look to be positioned right about here. Now that's the point in the domain, but we want to graph the point in the codomain. That point is going to have a modulus of √5, so it's going to be √5 high off of the flattened plane, off of the domain plane, if you will. And we're going to color it this magenta here. We have 3 spatial dimensions. 2 are used for the domain, 1 is used for the codomain. And then we use a color dimension to show what the angle is, or the argument is. Now, how do we come up with this sort of magenta? Well, let's look at the color wheel. The color wheel, if we lay perfectly flat here, would have an angle of 0, and that would give us real numbers. The horizontal axis is the real axis. If we go up by, say, 45 degrees, then in that case, we will have a number with its real and imaginary part being equal. If we were to go, let's say, pi over 2 degrees, or pi over 2 radians, pi 90 degrees, then we would get a purely imaginary number. Now what we have is that the angle is negative arctan of 1/2. That's roughly 31 degrees. That means we go down below the real axis, and that will take us to something that has both a non-zero real and imaginary part, and we see that it's kind of this magenta color here. Now, how do we get that 31 degrees? When we compute arctan of 1/2, unless you have switched your calculator or are using a site that uses degrees by default, we always have it be in radians. And we know that 180 degrees is the same thing as pi radians. And now if we just look at the unit analysis, radians divided by radians is nothing. Cancel those units, and we're just left with degrees. Simple computation gives us about -31 degrees. Because that puts us in the color wheel into this area in terms of its color, that's why we color it magenta here. Now there may be just some discrepancy between the color you see here and this. I'm a little limited in my color scheme, and the color that I see on the iPad I use to create these videos is a little bit different than what ends up in the video. So there may be some discrepancy, but I hope that I've explained it clearly enough that it makes sense why from here we would choose this color, or that there should be a match between this color and the angle we find in this color wheel. Now the original example graph that we showed was this here. You can alternatively also see graphs of complex functions in this way, where your height is now represented by this shading. So you use the shading to get a sense of the different heights and so on. So you can either flatten it and then represent the heights with shading, or you can represent it more three-dimensionally and actually show what looks like heights from a certain artistic point of view. The last picture on here, which I've not explained, is actually a picture by M.C. Escher, which is called Print Gallery. The reason this picture is here, besides Escher art in general is always pretty neat, is that Escher used a complex function, or was highly inspired by a complex function, to create this very distorted and interesting looking effect. For your reference, the complex function used was something like f of z is equal to z to the alpha, and then depending on how you manipulate alpha will cause more or less warping here. Now let's look at a property of complex functions that is the most important property. We say that a complex function going from D, where D is the domain and it's some subset of the complex numbers, we say that it's holomorphic at a given z value if and only if this limit exists. Now, this limit should probably be familiar to you. It's exactly the same limit that we saw when we looked at differentiating real valued functions. And indeed, another way to describe holomorphic is to say that a function is complex differentiable. This limit, if it exists, we call f prime of z, or we write f prime of z. And as noted, we can alternatively say that a function is complex differentiable in place of calling it holomorphic. These are synonymous terms. But for whatever reason, it seems like holomorphic is the more preferred term. Now that definition is all well and good, but without an example it can be a little hard to wrap your mind around what this means exactly. So let's consider a sample function that's defined as the following, where it switches its real and imaginary parts. So a complex number, x plus yi, is mapped to a complex number, y plus xi. The real and imaginary parts are split. We want to know, is this function holomorphic? And like we always must do when talking about holomorphic functions, we have to ask ourselves, where are we talking about? We want to know specifically, is the function holomorphic at this exact point? Now, just based on the definition that we just saw, we can observe that the limit that we needed to find, whether it exists or not, we can write that alternatively in the following way, where notice I've written h in its complex number more general form, where I split it into a real and imaginary part. The same is true here, where we have h1 plus h2i instead of just h. I substituted the specific z naught, which is 3 plus 4i. And now let's rewrite this a little bit, namely the expression in here, where we've combined the real terms and the imaginary terms. Alternatively, while we're at it, we could go ahead and determine what this value is simply by changing the x and the y to get this number. We'll find that the function of this number is just, again, switching the real and imaginary parts, giving us this here. We can do a little bit of algebraic manipulation, and we end up with this, h2 plus h1i divided by h1 plus h2i. I want to make note, if it wasn't clear, h going to 0 as a complex number is the same as saying both of its components are going to 0. So we're taking the limit as the corresponding h1 and h2 both go to 0. That's what it means for a complex number to go to 0. Now let's consider more closely what's happening with this potential limit. Now we want to find the limit or show that it doesn't exist. To do that, what we need to do is consider various paths for h1, h2 to go to 0. And when I say paths, I mean paths in the complex plane. Say we have the complex plane, where we have the real axis, or h1 axis, in this case, the imaginary axis, or the h2 axis in this case, and we consider a path, which we'll call path 1 for the magenta, path 2 for the green. We consider these two paths that will take us down to 0, 0, where h1 and h2 are 0. Now, there are many paths. We could have taken a squiggly path like this and so on, but we wanted just to consider two simple paths and show that we can possibly find that the limit doesn't exist. If we look at path 1, all along that path, h2 is 0, and then h1 is going towards 0, but h1 is not 0. However, that whole time along path 1, h2 is equal to 0. So if we take the limit along this path, where h1, h2 going to 0 means consider it along all the paths, so right now we're doing one very specific path. If we make the substitution, since h2 is 0, we get that the expression is h1i over h1. Of course, since h1 is not 0 while we're on the path, since we never actually set h1 equal to 0, while we're traveling towards 0, we can divide h1 by h1, leaving us with just I. Going along this path, we reach a limit of I along path 1. With path 2, notice here h1 is equal to 0 along that path, which gives us h2 divided by h2i, which is 1 over I. Multiplying the top and bottom by I gives us negative I. Now we've reached two different values going along two different paths. That means that this limit does not exist. In the very simplest sense, it doesn't exist because what do you choose for it to be? Do you choose I? Do you choose negative I? What if you take another path and it's 0? We can't pick just one thing because there are more than one, so that means the limit doesn't exist. Since the limit doesn't exist, this function is not holomorphic at 3 plus 4i. Now you could ask yourself, is it holomorphic other places? What about negative 2 plus 17i? Or negative 3 minus 1i, and so on. But here we happen to check it for exactly this point. Now let's say that we have a curve that goes from a real interval, a to b, into the complex plane. So a closed interval could be something like 0 to 1 or 7 to 322, whatever. It doesn't really matter actually. We just need some interval being mapped into the complex plane. This is the formal mathematical definition of a curve, and in particular we'll consider closed curves, where gamma of a is equal to gamma of b. That is, maybe we start out at some point, we move around the complex plane, and then we end up at the same spot. In order to manage this path, we'll parameterize it. We'll say that t is a given time, and the coordinates of this path are given also with respect to that time. So the real value can be determined at any given time in the interval, according to whatever the function is, and so can the imaginary value. Now I should say a little bit before going on. This is going to be moving pretty quickly through an important and advanced concept. I'm not expecting you to get many of the details. What we've covered up to before this slide is certainly things that I think are accessible and that you could work with right away. But getting here, we're now just looking at one of the core ideas of complex analysis. So don't worry about so many of the details here. Let's just try to look at the bigger picture for this part. So what we've set up is some curve in the complex plane, and that curve is called gamma. Here are just some points on that curve. Each one of these are complex numbers, such as a z naught, or whatever this blue and red point are. If we want to integrate, and here's where it might really seem difficult to follow, but again, focus on the big picture. Don't worry about getting all the little details at this point. If we want to do a line integral, which is a very important concept in calculus 3 and in complex analysis here. Sometimes these are called contour integrals. If we want to do this type of integral, we can represent it using this parameterization, which we can write like so, and then write like so. Now, this is just for your reference if you ever happen to watch this later or if you happen to know more mathematics. But the big idea, if you're just being exposed to this, is that we can do a line integral. That is, as we go around a path, gamma, we're going to trace out area. It's area that raises above or below that path in some sense. And we're going to compute that area. There's a little more to it because we're doing a complex line or contour integral. But this gives you maybe some sense of what you're doing. Instead of finding an area that may lay flat in the real plane, we've got something traced out that exists in a three-dimensional space or higher, but is yet still some kind of area. Now, Cauchy's integral theorem tells us the following. Namely, if we have an open, simply connected subset of C, and we've got a function that's holomorphic on it, if your curve is simple closed, rectifiable, then you get that the line integral is 0. So the notion is this. You have some area U. In that area, you have a simple closed curve. Your function f is holomorphic on this area U. And if you're holomorphic, then what you have is that the line integral is 0. Now, back at the beginning when we mentioned what complex analysis is about, we mentioned that one of the core discoveries was showing a relationship between the boundary of an area and the interior of the area. And here is exactly this. Doing a line integral around the boundary, we know that that line integral is going to be 0 without even having to compute it, so long as we know that the function is holomorphic on the interior. Information about the interior tells us what's going to happen on the boundary. And in other cases, if we know information about the boundary, we can determine what happens along the interior. So again, there's a relationship between boundary information and interior information, which is one of the core aspects of complex analysis and one of the things that makes it so cool. Let's look at dynamical systems, another cool area of analysis. First off, what is dynamical systems? It's simply the study of systems that evolve over time. That's really it. And of course, it should be no surprise that there are lots of applications for this. Human beings have cared about systems that evolve over time since as long as we've existed. Modern examples might include looking at the motion of stars and galaxies, changes in population, changes in the weather, the stock market, chemical reactions. Any case where time leads to some evolution of the system, that's dynamical systems. Now, what's the essential discovery of dynamical systems that makes it so cool? If you have a simple set of rules, deterministic, meaning you know exactly what they are, you know that every unit of time you're going to double a population. You can use simple deterministic rules, and yet this can lead to behavior that's so complex you can't even tell with any tools that it's not random. It is verifiably on the level of complexity as random behavior, which is amazing. So something very simple can lead to something very complex. A beautiful example of this is going to be the Mandelbrot set, which we'll work up to here. Now let's suppose we have a function capital F that is real input and real output. The domain is the real numbers and the codomain is the real numbers. We'll define a sequence of numbers, x0, x1, x2, x3 in the following way. We define xn to be the function of xn minus 1. That means if you want to know what xn is, you need to know what xn minus 1 is. This is an example of a recursive relation. Meaning if you want to find out what some value is, you have to go back, quote unquote, in some sense, to a earlier number or case or what have you, to find out what this new value is. You work backwards to find the current or new value. Let's say we start with a x0, and we'll let it be in the domain, so let it be a real number. We start by saying simply x0 is equal to x0, and another way to write this is that this is like we applied the function f no times. That's f to the 0, meaning we applied the function 0 times. That is, we have not applied it. The next case, for x1, using this formula, well, x1 should be equal to f of xn minus 1. So we take f of xn minus 1, since n is 1, n minus 1 is 0, so we get f1 of x of 0, and that's x1. To find x2, we take f of x1, f of the last thing, just like here we took f of the last thing. That's like applying f2 times to x0, because f of x0 is equal to x1. And another way to represent that is by saying f the second power of x0. We've taken x0, we fed it through f one time, then that number that we came up with, we fed it through f again. Finally, x3 is the same thing. To find x3, we look at f of x2, the last one. That's like applying f2 f of x1, which is like applying f to f of x0. That's like applying f 3 times to x0. And this would go on forever. But just to be really clear, if we take f of 5, let's say, of x0, we take x0, we feed it into f one time, whatever we get out, we feed it into f again, and so on until what we get out is f5 of x0. Now notice after feeding through once, we get f of x0. After feeding through twice, we get f squared of x0, and so on. And other ways to write these include this is x1, this is x2, this is x3, this is x4, and this would be x5. Taking a single starting value of x0 and continually applying f to it, that's called iteration. In this case down here, we've done 5 iterates. We've iterated it once, twice, 3 times, 4 times, 5 times. Let's say our function is x squared minus 1. Let's look at some iterates of different starting x0s. Say we have x0 of 0. We substitute that into our function. Of course, 0 squared is 0, subtract 1, and we get negative 1. Now take negative 1 and substitute it back into the function. That will give us negative 1 squared minus 1, which is 0. This is now what we call x2. Do the same thing again, where now we take 0 and we substitute it into this equation, and we'll get negative 1. And if you don't see it already, notice that all we can do is now alternate between 0 and negative 1. Because 0, when we substitute it in, gives us negative 1. Negative 1, when we substitute it in, gives us 0. So we're just going to flip-flop back and forth between 0 and negative 1. This, as we'll see shortly, is an example of a periodic point because it repeats. We go 0, after applying it 2 more times, we get back to 0, and so on. As is negative 1, because it repeats. Say we start with x of 0 being 1/2. We substitute in 1/2 into our equation. 1/2 squared is 1/4, minus 1 is negative 3/4. Then we take -3/4, substitute it into the equation, get our next iterate, and so on, so forth, and we get these numbers here. You can ask yourself, are these approaching a given value? I'll leave that for you to think about. Now let's try the golden ratio, which is 1 plus square root of 5 over 2. As a reminder, the golden ratio was a term popularized in classical Greek mathematics as a geometrically inspired number. Here, if we substitute in the golden ratio into our function x squared minus 1, we get back the golden ratio. Well, nothing should ever change from here on out. Substituting in this value gives us back the value. So if we do it again, we should get the same result. And again, should get the same result, and so on. This is an example of a fixed point. Substituting in the value gives you the value back. There's no change. Now let's talk about some definitions that we've alluded to here or mentioned briefly, and look at them with some formality. First, let's assume we have a function capital F that goes from R to R. And suppose we have a starting value of x naught. We call the orbit of x naught simply to be the series of iterates that we came up with. X naught, x sub 1, x sub 2, x sub 3, and so on. We just computed the orbits of 3 different values under the function x squared minus 1. We'd say a value x naught here is a periodic point if after some point it repeats. In our previous example, 0 was a periodic point because eventually it repeated. After 2 successive iterations, it returned to 0. So was -1. And the final example we looked at in the previous page was a fixed point. That is, if you substitute in the value into your function, you get the same value back. We saw that the golden ratio was a fixed point of that function. Again, the orbit is simply just the series of iterates you get. Now, one can do this numerically just by computing through with a table using Excel, but one can also do graphical analysis. Try to understand what the fixed points, periodic points are by looking at a graph. Sometimes that's more useful than numerical analysis, and other times it's less useful because it's not as exact. Sometimes the fact that it's not exact can be helpful. Sometimes it's not as helpful. Now we said that x equals 0 was a periodic point of x squared minus 1. If we want to find fixed points, we would say x squared minus 1, which is our function value, that's equal to x. This is a fixed point. We can alternatively then draw these two curves, and solving this equation amounts to finding out where these two curves intersect. We see that there's 2 places where they intersect, so there's 2 fixed points. And beyond that, we can find periodic points. We can find general behavior of points. Here's how we can see that x equal to 0 is a periodic point. If we start out at 0, if we substitute it into the equation, what we'll get out is -1, because 0 squared minus 1 is -1. That takes us from 0 down to -1. -1 is now what's substituted into the function again. In order to get there, we take -1 and we move it over to the identity line. Now, we can see that we're at -1 for our x value. We're below -1, and by below, I mean below the x-axis, below x equals -1. Substituting in -1 into this equation, what we get is 0, so that brings us back up to 0. And now the point of all this is that you alternate from the identity line. This would be the first place we start. You move up or down until you hit the function. Then you move back to the identity line, and then from the identity line back to the function. So you're oscillating between the identity line and the function itself. This is because we're doing iteration. We started with x is equal to 0. We found that the value is -1, and in order to substitute that back in, we want to move back over to the identity line. Once we've moved back over, we can resubstitute it back in, which amounts to just following up until we hit the function graph here. Notice if you tried to do the same thing for the fixed points, say here and here, we wouldn't be able to get anywhere playing this game. Going from the identity line to the function line, it's just going to take us to the same point, and then we're going to go back to the same point, and so on. We don't get anywhere. Suppose we start at this point. We substitute this value into the equation, which graphically amounts to moving until we hit the function line. Then from there, we reset ourselves back to the identity line, and then continue this process, and maybe you can see what's going to happen. Then we're going to be moved back to here, like so, and we may kind of spiral around here, and so on. Again, where graphical analysis in this case is not as helpful is in making sure that we would, let's say, get closer and closer to the fixed point that we saw earlier. But it's really helpful at giving us a very quick idea roughly what's going to happen. We know we're going to move through this area and end up around here. So in some sense, we can get information much faster, but we just can't be quite as accurate. Now suppose that we want to see what's going to happen in this region. We focus on it and then blow it up. If we start, let's say, in this region, we can see what's going to happen. We're going to move up, over, and so on. And that should continue forever, meaning these iterates are going to get larger and larger and larger, and just go off to infinity. Now, as we noted, there are two fixed points, 1 plus root 5 over 2, and then 1 minus root 5 over 2. These can be found using some simple algebra. Just set x squared minus 1 equal to x. You have a polynomial, second degree in x. You can use the quadratic formula. What we want to look at here is what happens to these fixed points. Let's fill in what will happen to some representative points that are near the fixed points in this region, and over here. Let's see what happens to them. In this region, as we saw, a point that starts near the fixed point, but let's say a little up and to the right, will escape off to infinity. A point that starts near the fixed point up here, just a golden ratio, but maybe a little less than it, will move down towards the other fixed point. Might be a little hard to see, but points that start near this fixed point will be pulled in towards the fixed point. A fixed point that repels points away from it, we call naturally repelling fixed point. That is, points close are moved away. And then a point that pulls in orbits around it or points around it, we call that an attracting fixed point. So the orbits move away from the fixed point, or the orbits are pulled in towards the fixed point. Now I've just given an intuitive idea about what it means to be a fixed point that is repelling or attracting. But my question to you is whether you can make this more formal. That is, can you construct a mathematically rigorous definition of what it means to be an attracting or repelling fixed point? So that's two different definitions, one for attracting and one for repelling. It's kind of a neat little exercise. Now let's get into defining the Mandelbrot set. Let's start by having a uppercase f sub c be our function that goes from the complex numbers to the complex numbers, and it's defined in the following way. For a given complex number z, you take and square that number and you add c to it. Then we'll define m by the following way. Your complex number c is either mapped to 0 or 1. It's mapped to 0 if the limit, as you iterate your function, and notice we're going to take the absolute value here, and that absolute value is equal to the modulus. Remember, we're looking at complex numbers, so think back to what we talked about in complex analysis. We're taking the modulus, which is itself a non-negative real number. If that limit of these non-negative real numbers, if it's not equal to infinity, then we define that c value to be mapped to 0. Now, it doesn't have to even exist. It just has to not be infinity. So it can bounce between two values. It could go like 1/2 to -2/3, 1/2 to -2/3. It could oscillate or do a variety of things. It could never settle in on a given number. But as so long as it does not go to infinity, we then say C is assigned to 0. If it does go to infinity, then we say it's assigned to 1. So it's binary. It's assigned to 0 or 1, depending on whether, as you iterate, it's bounded, it doesn't go off to infinity, same thing, or it does go off to infinity. The Mandelbrot set then is simply the preimage of 0. That is all the complex numbers C such that the M value of C is equal to 0. It's just all the complex numbers such that as you iterate them under this function, it does not go to infinity. Complex numbers that are in the Mandelbrot set are colored black. So all this in here is in the Mandelbrot set. All this is, this part of that real line there is, this part up here, and so on. If MC is equal to 1, we certainly color it red. And we have these differing colors just to make it a little easier to see what's going on, but everything in black is what is in the Mandelbrot set. Sometimes this is alternatively defined to be the boundary, but we'll take it to be also the interior here. I should reiterate that this is happening in the complex plane. All of these are complex numbers. Now, we aren't showing the axes just for the sake of presenting a more pretty picture. But let's now put the axes in so we can see more concretely what we're looking at here. Now we've drawn in the axes where we have the red real axis, and then we have the imaginary axis in cyan here. And we've plotted two numbers in particular, two complex numbers. One is in green, this 1 plus I. Now if you take 1 plus I and you substitute it into the f of 1 plus I, or f sub 1 plus I, eventually those iterates will go off to infinity. Hence why m of 1 plus I is 1, and hence why it's not in the Mandelbrot set. Alternatively, if you take a point, let's say -4 plus 1/5 I, then in that case, the Mandelbrot value, if you will, or the m value, is going to be equal to 0. You take successive iterations, and they will never go off to infinity. Let's show some calculations that you might use to be able to determine whether something's in the Mandelbrot set or not. Let's start by taking the point -1/4 plus 1/5 I, and let's substitute it into the function, which is f sub -1/4 plus 1/5 I. If we do that, we substitute it in. That means we're going to take this value, square it, plus the same value we compute to get this value here. And now if we take the modulus of this complex number, we get this here. Continuing with this function, f sub -1/4 plus 1/5 I, but now substituting in this value, we get the following. So we substitute in a new value, which means we square that value, but we still add the value we started with, which is here. We get this computation, and taking the modulus, we get this. Doing it one more time, where now we're going to take and substitute this into the function, will give us this here, modulus like so, and we would keep going. Now this was an example of doing by hand 3 iterations. We started with this complex number, the first iteration gave us this complex number, the second iteration gave us this, the third iteration gave us this, and we would continue so on and so forth, finding the moduli to be these. Now if it seemed like these numbers kept increasing without bound, and eventually you'd get to 10, eventually you get to 100, eventually you get to 1,000, and you just keep getting larger and larger and larger, and it goes off to infinity, that would show that it's not in the Mandelbrot set. We've shown with our Mandelbrot diagrams that it is. So what that means is this will always stay bounded. That is, there's some real number we can always say it's less than, and some real number we can always say it's greater than. Now let's look at some trippy images involving the Mandelbrot set. So one of the interesting things about the Mandelbrot set is its self-similarity. That means you can zoom in, and it keeps looking the same as itself. So as you zoom in, you look at smaller parts of it, but these smaller parts look like the bigger parts, which is very cool to me. And there are other things called Julia sets, which are defined similarly to the Mandelbrot set. And you can get all sorts of beautiful shapes. You can get fractal behavior and lots of really, really pretty stuff here. Now, this is an example of how we get something very complex from really a simple function. All we were doing was we were taking, squaring a complex number and then adding another complex number to it. That's it. That's a simple complex polynomial. And from that, we get this very weird, twisted, complex, cool behavior. Now, the next part of this video is going to be on ordinary and partial differential equations, but it won't be me talking to you about it. Instead, it will be a friend of mine, Dr. Niles Armstrong, who has done research in partial differential equations.
Hello everyone, I am Dr. Niles Armstrong. I am an assistant professor at Milwaukee School of Engineering currently. Now, what you are looking at is what is obviously my old and outdated personal web page. This is serviceable, so you can see a sort of ridiculous, cheesy photo of me, so you can put a face to the voice. And over on the left-hand side, under my research interest, you can see that I do or have done research in elliptic partial differential equations, which is a large umbrella term, along with free boundary problems. Now, really what I want to talk with you a little bit about today is just the field of partial differential equations, or maybe even more broadly, just differential equations in general. So what are differential equations? What are they good for? And maybe what is it like to do research in the field of differential equations, or maybe partial differential equations? So first things first, what is a differential equation? So it's really quite simple. It's an equation that has derivatives in it, a derivative or many derivatives. In the case of partial differential equation, it can contain partial derivatives, if you're familiar with that. If not, don't worry too much about it. But that's it, an equation that maybe involves the function and 1 or 2 or 12 derivatives of that function. So the simplest, or one of the simplest differential equations you could look at to maybe be one of the following. Let's suppose I have some function f, and f is a function of x here. And what I've written down here is a very simple differential equation. So it says that the derivative of f with respect to x is equal to f of x. Okay, so that's it. It's an equation. It has a derivative in it and the function itself. That's a differential equation. Okay, so this is a very simple differential equation. And in fact, probably one that you can think of a function that would satisfy this differential equation. So think for a second. Do you know a function so that when you take its derivative, it spits the function back out? Nothing happens. Well, if you think back to your Calc 1 days, you may eventually come up with the answer or an answer of just e to the x. And in fact, this is true. This is what would be a solution to this differential equation. Here's a function whose derivative is equal to itself. In fact, there are many solutions to this differential equation. If we multiply any constant we want in front of here, in fact, let's just say c e to the x, these would all be solutions as well. So great, there's a differential equation. Here are a bunch of solutions to it. Hooray. So why is there an entire field of mathematics, or really many fields of mathematics, dedicated to studying such equations? Why would I spend my, lifetime studying such things if all it is just, hey, solve this equation? Okay, well, first of all, this is a very simple example. And second of all, these types of equations are extremely important, not just in mathematics, but in the world of science at large. When you think, what are derivatives after all? They are rates of change. If you think about what people study in science, what we observe, what we can measure, it's change. So if we want to use mathematics to describe science, to model science, if we want to use mathematics in a sort of powerful and meaningful way to model this change that we're very typically seeing, we're going to be using derivatives. So once we have derivatives involved in the equation, differential equation. Differential equations, again, these can model tons and tons and tons of phenomena that happen in our world. Things like gravity, fluid motion called fluid dynamic, heat flow and diffusion, quantum mechanics. It can be used to model electrical circuits, population dynamics and changes. So differential equations show up just really absolutely everywhere. Now, when you hear all that, and certainly when I took my first ordinary differential equation class, it gave me this feeling that, oh, differential equations is a very applied mathematics. All right, it's very applicable. It's all about these applications. You can model systems with it, and you can solve these systems, and that tells you something about the system in the future, which is very, very powerful. And while that is certainly one type of research that you can do with differential equations and partial differential equations, you could be an applied mathematician that's interested in that stuff. It's certainly not limited to the strict applications. In fact, I would consider myself to be a pure mathematician, even though I study partial differential equations. How does that work, and what does that even look like? What I study, if you're, interested in more the, pure side of, partial differential equations, I would study a more general type of a differential equation instead of a very specific one like we saw up here. In fact, one of the differential equations that has been very important to me in my work would look something like the following. It would look like the divergence of a of x, gradient f of x, equals 0. Okay, and if you haven't heard about the gradient and the divergence before, don't worry too much about it. The point is that this differential equation, and really this is a partial differential equation, this is a very non-specific differential equation as opposed to the one above. And really that's because of this a of x right here. What this is, the a of x, this is some matrix. All we know is this is some matrix. We're trying to find our solutions, this f of x here. But for different matrices that we plug in for A, we have a totally different differential equation. And so as opposed to this sort of take a differential equation and solve it mentality, we can't really do that here. If I don't specify what A of x is, I can't really solve for f of x, not explicitly. So what are we interested in when we study this sort of general form of a differential equation? We're not interested in just solving the equation. That's not the goal, right? Because we can't. So instead what we're interested in are really, what can you say about the solution, right? And oftentimes we're interested in things like regularity. And what I mean by that is, how nice is f of x? Is it continuous? Is it differentiable once, twice, 3 times, 4 times, not at all, right? What kind of a function is f of x? How nice is it? And really before I get to regularity, there's actually a more important question. Does f of x exist? Does it exist at all? Is there a solution to this equation? That's called the existence question, which is one of the primary questions you would ask when first studying a PDE. The last one here is, given some initial, say, information, usually we call this an initial condition, but given some initial information about f of x, is the solution unique? So really these two questions together are the big existence and uniqueness question, which is sort of the first thing you would want to study or want to answer when talking about a differential equation. If you're about to study this differential equation in depth, you first need to know if it's worth your while. If you have a differential equation that, doesn't have solutions, well, you may need to rethink the differential equation you're looking at. And maybe worse than that, no, not worse than that, but also bad, would be, are the solutions not unique? Given some initial conditions, do you not have unique solutions to this? That would mean if you have this differential equation modeling some system, and you turn the system on, you still don't know what happens because there are multiple solutions, right? The solutions are not unique. And so that's just, well, it's not very useful. Now that happens, and it can still be interesting and it can still be studied. But these are sort of important questions you would talk about. That's the type of stuff that you would study, and really just a small snippet here, but this is sort of some of the type of stuff you would study in partial differential equations, really before you even got to solving these differential equations to begin with, right? These are some of the more big fundamental questions you would ask yourself about certain types of PDEs. Right? What can you say about your solutions? Do they exist and are they unique? Right? These are some of the big ones here. And these are some of the things that I am typically more focused on. Now to hone in a little bit more on my own research, the stuff that I talk about is really more narrow in that it is interested in a very powerful tool that is used in answering these types of questions that I have here, right? And this very powerful tool is called the mean value theorem. Now, I won't write the mean value theorem down because it's plagued with a bunch of notation that probably won't serve to be that useful to us at this point. But the mean value theorem, and maybe let's start here, mean value theorem, NVT, is an extremely important theorem in the study of what are called harmonic functions. So let's say very important for harmonic functions. And I'll mention what these are here in a second. But I should also say this is not the mean value theorem that you probably learned in calculus. This is obviously a little bit different in that we're in the land of partial differential equations. So that name may sound familiar to you for those of you who have made it through your calc, but this is something slightly different. So the mean value theorem, this very important theorem for harmonic functions. Now, harmonic functions are functions that satisfy the following differential equation. That's the Laplace of the function is equal to 0. And really, I should mention here this notation. What does this mean? This is the sum of the pure second partial derivatives. Okay, and again, if you haven't seen second partial derivatives before, don't worry too much about this. So for example, if I have a function of x and y, this would be what the Laplacian looks like. But either way, this is a harmonic function, and these are very, very, very important functions in application. I won't go too much into that for time's sake. But the mean value theorem for these harmonic functions says that the value of a function at some point, x naught, is equal to the average of f of x on any, and this is important, any ball centered at x naught. That's essentially what the mean value theorem says for harmonic functions, and this is a wildly miraculous theorem, or really property that happens for these harmonic functions. You start centered at this point x naught, and you take any ball you want. You take any circle, or any ball around this point x naught, and you take the average of this function, this harmonic function. That average is equal to the value of the function at the point x naught. And it doesn't matter what ball you drew. As long as it's centered at x naught, the average is equal to the value of the function at x naught. This is a super, super, super important tool in the study of harmonic functions, and it gets used to answer a lot of the questions here about regularity of these functions, these harmonic functions. Okay. Now, this is very well studied. This is not what my research lies in, but if you ever study elliptic partial differential equations, this is actually probably the first thing you learn. Super important. So what do I study? Well, I study something that I like to call the generalized mean value theorem. Now, this was a theorem that my advisor had a hand in proving, and his advisor was the one that actually touted its existence to begin with. But what it says is, if we look at what I like to call generalized harmonic functions, which are functions that satisfy, well, this equation I had written up before. So these are my generalized harmonic function. So if I have a function that satisfies this equation, then I get something similar, that f at some point x naught is equal to the average of f of x over any set from a particular family of sets. Okay, so the stark contrast here is, before I said the average of f of x over any ball centered at x naught. It was very specific. And here, the average is taken over some set. Right? And so what we have here is this x naught, and the average is taken over some set here. And maybe if you want the set to be bigger, maybe it looks wildly different. Now it looks something like this. And that in lies the problem with this generalized mean value theorem, and really where my research comes in. It's very similar to the original mean value theorem, and it can be just as powerful when we want to study questions about, say, regularity of these generalized harmonic functions. But what we have to get a better handle on is this from a particular family of sets. What are those sets? Well, they depend heavily on this a of x up here, right? And some of the stuff I look to answer, questions I look to answer, are what can I say about these family of sets, maybe given some information about a of x. The more that I can say about these sets, then the better this generalized mean value theorem becomes, which makes it a better tool for studying these generalized harmonic functions. Okay, so that's sort of the very briefest, easiest synopsis I guess I could give of my research. And these are the questions that I look at tackling when I sit down to do my own research. If you get a chance to take a course in PDEs, I certainly suggest that you do. All right, well, thank you all for your time.